Make sure you have all three things that are on the board in your notes. This will help you whenever we get to those notebook quizzes at the end of every chapter. You need to know that this is section 1.2. This section is all about inductive reasoning, and our objective today is to use inductive reasoning to make conjectures. You might be saying to yourself, I don't know what inductive reasoning is. I don't know what a conjecture is. We will talk about those definitions in a second, so for right now, just write them down, even if you don't know what they mean, and we will get there. Here's some vocab that you need to get started on today's lesson. The two words we're going to talk about are conjecture and inductive reasoning. A conjecture is an unproven statement based on a pattern or observation. Most of what we do today is completing conjectures. So we are going to try to observe patterns that appear in different type of examples of math problems. And then inductive reasoning, we were using this skill yesterday as well. It's the process of looking for patterns and making observations. A lot of what we do in math class is noticing a pattern, using it to make predictions or observations. So go ahead and get these definitions down, and we'll start looking at some examples. We are only going to get to about 3 examples today. These take a pretty long time. They're a bit on the challenging side, so if you feel a little overwhelmed, you are not alone. This is a skill that takes some students a while to pick up on. But please stick with it and just raise your hand if you're feeling lost, and I will try to slow down a little bit. So there's a lot of words popping up. You do not need to write these, but this is something that I want you to keep in mind. These are the steps that we're going to follow when we are reasoning through today's problem. So the first thing we want to try to do is notice a pattern. We're going to look for a pattern. We do this by looking at several examples, using a diagram or table if we're having a hard time discovering the pattern. After we notice a pattern, we are going to make a conjecture. Use the examples to make a general conjecture. Modify it if needed. So sometimes you'll think you have the right conjecture, and then someone will think of an example that proves you wrong. So we might have to change your conjecture. Then we're going to verify the conjecture. So use logical reasoning to verify the conjecture is true for all cases. So typically I like to think of 3 examples and then try to make a conjecture from there. And then I try to think, can I think of another example that proves this one wrong? If you cannot think of an example that proves yourself wrong, then you probably have the right conjecture. Any questions on those 3 steps? Again, you do not need to write these down. I think it's a lot of writing for a process that's probably just going to happen naturally as we go through these problems. Any questions? You do need to write these down. These are the 2 parts of example 1. We are just going to make a conjecture. Make a conjecture is basically a fancy way to say complete this sentence. We are going to complete this sentence by thinking of examples and noticing a pattern. Now, some of the hardest things to figure out when you're making conjectures is just old vocabulary words that you might have forgotten. So let's talk about some of those words as you're writing them. What does sum mean? Addition. So I'm just going to put a little plus sign above sum so I remember that that means addition. What's product mean? Someone said subtract. Subtract is the word difference. You will see that today. Difference means subtract. Quotient is division. Multiply. You can show multiplication using the dot or parentheses, or you can just write the word multiplication. But product means multiplication. Integer is basically a positive or a negative number. So we'll have to make sure we're thinking of positives and negatives. We talked about n yesterday. N can stand for what? Any number. Very good. So before we start thinking of examples, I just want to clarify some of those vocabulary words that are appearing. Any questions before we get going? Alright, so part A says the sum of any two odd numbers is blank. So I'm going to think of a few examples where I am adding odd numbers. Someone spit out an odd number. 5. Give me another one. 7. Okay, 5 plus 7 is 12. Someone give me another odd number. 3. 1. 3 plus 1 is 4. Give me some more odd numbers. 9. 11. What's 9 plus 11? 20. What are you noticing about all the answers? They're even. That is my conjecture. That when you add two odd numbers, you're going to get an even number. That's it. Any questions on part A? Alright, part B, we are going to be multiplying, so I'm going to set up 3 lines of a multiplication problem. I'm going to use the dots. Someone give me a number, n. Give me an n. 6. What's the opposite of 6? Anyone know? Negative 6. What is 6 times negative 6? Negative 36. Good. Okay, that's one example. Give me another n value. 7. The opposite of 7 is negative 7. What's 7 times negative 7?
Negative 49.
Negative 49. Very good. Can I get another one? 12. What's the opposite of 12?
Negative 12.
And 12 times negative 12 is negative 144. What are you noticing about all these answers?
The answers are all negative.
Negative. That is my conjecture. Very good. So again, we are thinking of examples, making a pattern, describing it in words. What are your questions so far? Remember, if you can't see the pattern emerging right away, we might need to do a table or some sort of diagram, but these were both a little easier to see. Any questions? All right, here's example 2. Again, it has 2 parts. I'll give you a second to write it down. Remember, we are seeing that same word product. Product means multiply. We are also seeing n. N just means any old number you can think of. Alright, so part A, we're doing a product. I'm going to use parentheses this time, so I'm going to set up some blanks, and I'm going to fill them in as I go. And I'm only filling them in with odd numbers. Someone tell me an odd number. 3. Give me another one. 5. 3 and 5 multiplied together gives me 15. More odd numbers. 7 and 9. 7 times 9 is 63. Give me more odd numbers. We haven't done any negatives. Someone give me a negative odd number. Negative 11. Give me another odd number. Negative 5. Negative 11 times negative 5 is, oops, positive 55. What are you noticing about all of these products? When you're multiplying two odd numbers, your answer is? Odd. Someone said positive. So far, they've all been positive, but what if we did negative 11 times positive 5? Then we get negative 55. So I can think of, we call this a counterexample, an example that proves your conjecture wrong. If you can, then you need to redo your conjecture. So I can think of an example that would give me a negative number. So although my first three, it did look like they were all going to be positive, I could disprove it very quickly. But I cannot think of an example where two odds multiplied together gives me an odd, so I am going to stick with this conjecture. What are your questions? All right, this next one's kind of tricky, so bear with me. Remember, n is just going to be any old number, and I am multiplying n minus 1 and n plus 1. So when you guys give me a number, I will write it out, that number minus 1 times that number plus 1. I'm going to do that 3 times, and I'm going to see if I can notice a pattern. Someone give me an n. 5. 5 minus 1, 5 plus 1. You have to keep the n the same for that entire example. Both of the n's need to be the same number. 5 minus 1 is 4. 5 plus 1 is 6. 4 times 6, 24. So when n equals 5, my answer is 24. All right? Anyone have another one? What number are you plugging in?
8.
8. So 8 minus 1, 8 plus 1. That gives me 7 and 9, which is 63. So when I make n equal to 8, I get 63 as my answer. Good work so far. Let's try one more. Let's try 0. Everyone always forgets 0 and the negative, so I'm going to do 0. Whoops. 0 minus 1 is negative 1. 0 plus 1 is positive 1. Negative 1 is my answer. So I have an even number when I plug 5 in, I have an odd number when I plug 8 in, and I have a negative number when I plug 0 in. So I'm not noticing a pattern right away. They all seem unrelated, to be honest. Let's draw a little diagram. So when I made n 5, what was my answer? 24. When I made n 8, what was my answer? 63. When I made n 0, what was my answer? Negative 1. So 5 gives me 24, 8 gives me 63, 0 gives me negative 1. Anyone think they have any ideas? It's a little more sophisticated than our previous examples. Would you like a hint? What's 5 times 5? What's 8 times 8? What's 0 times 0? What do you know about those answers? 5 squared is 25, 8 squared is 64, 0 squared is 0. Our answers are all
same number.
yeah, you're multiplying the same number by itself, so you're squaring the number, and then what are you doing to it? Five squared is 25, but our answer was 24. How does 24 relate to 25? Perfect. You take whatever the n value is, you multiply it by itself, that's called squaring it, and then you take 1 away. That's our conjecture. So if you plug 10 in, instead of plugging it in for n, subtracting 1, adding 1, multiplying, you could use this new pattern. So if I plug 10 in, I should get 100 minus 1, which is 99. You could check it and see if it works. It does. This one was very hard. This is what I consider more of a group type problem, so we can discuss it and bounce ideas off of each other. I am not expecting you to do a problem like B on your own yet. Any questions? Good work. Okay, I have one more vocab word for you. We've already sort of talked about this. It's a counter example, and you do need to write this in your notes. A counter example is an example that shows a conjecture is false. You don't need to write what's in parentheses, but basically we are proving that the conjecture is false. Now, counterexamples are probably something you use with your friends all the time. You don't even notice you're doing it. So what if I said, all the school lunches here are really good? Did you instantly think of one that wasn't good? That's a counterexample. Is there one here that's not so good? The pizza. Okay, so if I said, all the school lunches at Belleville East are delicious, you'd say, no, they're not. The pizza here is horrible. That's a counterexample. Or, all the teachers here are so nice. Don't say anyone's name out loud. And you instantly think of like the meanest teacher you've ever had. That's a counterexample. So you use these all the time. You don't even realize you're doing it. Anytime you're disagreeing with your friends or your parents, you're probably thinking of counterexamples. Okay, here is example 3. I want you to just pick one of them to do in your notes. Pick A or B. We'll do them both on the board, but just to save time, pick one and write it down. I'm assuming you're all going to pick B because it's shorter. So the directions say, show the conjecture is false by finding a counterexample. I will tell you the biggest trick to counterexamples is the number 0 and negative numbers, because we always forget about those. So if you're feeling stuck, try using negatives and see if it helps. Or try using 0 and see if it helps. Again, you only need to pick one, A or B, and write it down. Part A, the conjecture is the sum of two numbers is always greater than the larger of the two numbers. So when you add two numbers, you always get a bigger number as your answer. Can you think of a time when that will not be true? Do you remember my hints? My hints to you are try zeros and negatives. Someone give me a negative number. -2. So I'm going to try the two things that usually help you with counterexamples, zeros and negatives. The sum of 0 and -2 is -2. Is -2 greater than 0? It is not. This is a counterexample for this problem. I just proved their statement to be false. I thought of two numbers that I could add together that did not give me a larger number than the numbers I started with. Part B, the product of two numbers is even. If the product of two numbers is even, then the numbers must be even. What's the opposite of an even number? Odd number. Somebody give me an odd number. 5. So I'm going to use 5 in my counterexample. Can you think of a number that you multiply by 5 and you get an even number as your answer? 4. 5 times 4 is 20. That's a counterexample. I just proved that I can get an even number using multiplication and an odd number. Done. What are your questions? Now, I understand that this is a very difficult section, so we are going to do a few of your homework problems together. So as you're finishing up your notes, I'm going to give you your homework. Make sure you keep it out because we're going to do a little bit of it on the board. So we are going to do a few examples on the board, and this is from the 1.2 worksheet. So I'm just going to start at the top, example 1, or problem number 1. The directions say complete the conjecture based on the pattern in the examples. Number 1's conjecture is the product of any two even numbers is blank. Now, in our notes, we came up with all the examples, but your homework actually gives you 6 examples that you can use to try to finish your conjecture. So, they are multiplying even numbers, and we are trying to figure out the answer is always what. So, they show us that 4 times 2 is 8, 6 times 10 is 60, 8 times 4 is 32, 10 times 10 is 100, 4 times 12 is 48, 22 times 20 is 440. What are you noticing about all the answers? They are even. Alright, let's just keep on going to number 2. The sum of any two consecutive whole numbers is a blank number. Now, you might be wondering what two consecutive whole numbers mean. That's just two numbers in a row. So like 2 and 3, 4 and 5, 6 and 7. But again, they're giving you 6 examples. You can go off those. When you add 3 and 4, you get 7. When you add 5 and 6, you get 11. When you add 9 and 10, you get 19. When you add 10 and 11, you get 21. 16 and 17 gives you 33. 23 and 24 gives you 57. What are you noticing about all the answers?
They're odd.
Odd. So when you add two consecutive whole numbers, your answer is going to be odd. After you make those conjectures, think if you can find a counterexample. I can't find a counterexample to either of those, so I am confident with my work here. Now, I'm going to have you do 3 and 4 on your own, but not right now. Skip down to number 5. The directions for number 5 say, in exercises 5 through 8, show the conjecture is false by finding a counterexample. So 5, 6, 7, 8, we are just listing a counterexample. That's it. Number 5 says, if the 3 corners of a triangle all touch the same circle, the sides of the triangle must be equal. So basically I'm going to try to put a triangle inside of a circle, and I'm going to try to show that the sides don't have to be the same length. The way you do that is you make one side really short and you make one side really long. Those will probably not be the same lengths, right? That's all you have to do for number 5. Basically, just don't put a triangle inside of the circle like this. That looks like they could all be the same, right? Just draw one that's not quite centered perfectly so that we know all the side lengths are different. All right, let's pick another one from that section. Any preferences, 6, 7, or 8? 8. Number 8 says, the difference of 2 positive numbers is positive. What does difference mean? Subtract. So we are trying to think of a time when you subtract 2 positive numbers and your answer isn't positive. Well, let's just start guessing. Give me some positive numbers. Do you have it? What do you got? 1 minus 0. 0 is not a positive number or a negative number, so let's not do 0. 1 minus, give me another positive number. 2, I heard someone say. What is 1 minus 2? Negative 1. I just subtracted 2 positive numbers. I got an answer that was not positive. So I just proved it wrong. Now, the key to number 8 is as long as you put the bigger number second, you'll end up with a negative answer. So you could pick any 2 positive numbers, just put the bigger one after the minus sign, and your answer will be negative. All right, so I want you to try 6 and 7. Let's look at number 9. Number 9 is an interesting word problem. This says, Jose is a child living in Argentina where spring begins in September and ends in December. Because he sees the days getting longer in these months, he makes a conjecture that the days are longer all over the world. Show that Jose's conjecture is false by writing a counterexample. So he is saying that the daylight hours get longer and longer and longer through the months of September and December. Is that true for us? No. When is the shortest day of the year? Anybody know? It's right before. Anybody know? Right before the biggest holiday of the year? Christmas. Yes, the shortest day of the year is in December. That is proving Jose wrong. Jose is saying the longest days are in December. The reason is he lives in the different hemisphere. They have different seasons there. September through December is actually our fall time. We know that the sun sets earlier and earlier in the fall. So my counterexample is that the shortest day of the year is in December. That wasn't even really a math problem. That was more of like a geography, social studies type problem. So that's why I want to do that one together. So you currently have 5 problems done on your homework for tonight. 5 out of 10. You got 50% of your homework done. Any other questions that you're like, I am never going to get this unless she does it on the board right now? Number 6. I'll give you guys a bonus. Number 6. Number 6 says, if the product of two numbers is an integer, then both numbers must be integers. Integers are positive and negative whole numbers, including 0. So basically not fractions and not decimals. The product of two numbers is an integer, then both the numbers are integers. What did I tell you were the really, really good things to remember when you're doing counterexamples? Negatives and 0. Let's multiply 0 by something that's not an integer, meaning a fraction or a decimal. Someone give me a fraction. What? 1/4. What is 0 times 1/4? What's 0 times anything? 0. This is an integer. This is an integer. This is not an integer. So I just got a counterexample for 6. Thank you for asking 6. I think the vocab in 6 would have definitely screwed you guys up a little bit. All right, so you have 4 problems on the homework to finish on your own. If you get stuck, please ask an adult. Please ask a teacher. Please ask a friend. Sometimes just reading the problem out loud to another person will help you figure out what's going on. Let me know if you need anything.